Hey everybody! So today we're going to start to talk about atomic weight. And you started to get a look at atomic weight today when we were doing that lab involving the fictitious element benium. So in your sample of benium, every single particle in there was a bean, right? However, I added just an arbitrary amount of the three types of beans. So there were lima beans, pinto beans, and navy beans. All beans, but they all had different weights to them. They all had different masses. And that's because they're three different types of beans. In the same way that atoms all have different isotopes, or elements have different isotopes, I should say. For example, carbon comes as carbon 12, but it also comes as carbon 13 and might also come as carbon 14. All the same element, but with different masses. In the same way in your sample today, they were all beans, but they were all different size beans in the same way that elements have different masses as isotopes. And in each of your samples, there was a different amount of each of the types of beans. That's how chemists are able to calculate the atomic weight of an element on the periodic table. So when we were calculating protons plus neutrons equals mass number is always going to be a whole number. And sometimes students will ask me, well, why is the mass on the periodic table different? Why is that not a whole number? For example, why is chlorine 35.45 when its mass number is either 35 or 36? That's where atomic weight comes into play. Chemists are able to find a weighted average of one individual atom, a weighted average of one. In the same way, in your lab that you did today, based on the percentage of each bean in the sample, what's the average mass of just one bean? And the reason why chemists do this is because it's very hard to calculate the mass of one atom. So considering the percent abundance of each isotope, we can find a weighted average. What would the mass of one atom be? And that's what this is. So it's the average mass of atoms of an element, and it's calculated using the relative abundance of isotopes in a naturally occurring element. Another example that we can think of is finding the weight of the average American, let's say. So an American might weigh approximately 175 pounds. Now, we have to consider, well, so much of the population is underweight, so much of the population is in the right frame, I guess, is okay. I don't know, is average. And so much of the population is obese and so much is morbidly obese. Each one of those categories, based on their percentage, contributes to the average mass of one American, right? So if 15% is underweight, 70% is average, and then the remainder is going to be overweight, we have to consider the percentages of each one to find the mass of one single American. However, it's very difficult to find the mass of one considering the whole because there are a lot of Americans. In the same way that when we're talking atoms, there are a lot of atoms in a sample. And based on the percents of each isotopes, we can find a weighted average of just one. Now, no one atom equals the mass on the periodic table because, again, every one atom is a particular isotope with that mass. So therefore, an element will never match the atomic weight on the periodic table, which is kind of interesting. But on average, what's the weight of just one atom? And there's 3 steps to calculate the atomic weight. So what we're going to do is find all of the masses that are listed on the periodic table, essentially. So why does chlorine have an atomic weight of 35.45? Well, we have to consider the relative abundances of each isotope of chlorine. So how do I do that? Well, you're going to be given the percent abundance first. So first you have to divide that percent abundance by 100. It's a very easy calculation. You might not even need a calculator for that. The second step is for each of those isotopes, you want to multiply your answer from step 1 by the appropriate atomic mass. So you're going to be given the atomic mass. So you might be given all of the isotopes present for a sample, and you are given their masses. So whatever mass corresponds to that percentage, you're going to multiply those two values together. And then lastly, you're just going to add up the products from step 2 to get the atomic weight. So once you add those together, your atomic weight should equal the mass that you find on the periodic table. And again, atomic weight, atomic mass, molar mass, they all kind of mean the same thing. I don't know why chemists like to have 80 different names for the same exact number, but unfortunately, that's the way it is. Let's go ahead and do an example. So here is sample problem 3 that we'll do together. Neon has 3 naturally occurring isotopes. So neon exists in nature as neon 20, we have neon 21, and we also have neon 22. Given the following abundances of these isotopes in nature, what is the atomic weight of neon? So you should be able to look up the answer for this on a periodic table before we even get started. So the atomic weight for neon, if I just look on this page before, is 20.180. And I'm just going to keep that here because I know that that has to be my answer. We're showing how do we get these atomic weights on the periodic table from these atomic masses of nuclides. No one atom has the mass of the atomic weight on the periodic table. This is a weighted average. We're considering that if I had so many particles in my hand, on average, what's the mass of one of them? So this is where this is coming from right here. So let's go ahead and just calculate the atomic weight, and hopefully we should get this answer. So first things first, we're going to start with the percent abundance. So I'm just going to copy those down underneath it. 90.48, 0.27, and I have 9.25. First step is we want to get them out of their percents. So we are just going to divide by 100. I like to do these in rows going straight across. It really doesn't matter how you do it, but I like to keep things nice and streamlined. You probably don't need to use a calculator for that. And you get those values right there. So you just divide it by 100. The next step is you want to multiply by the appropriate atomic mass. So this 90.48 corresponds to the atomic mass for neon 20. So I'm going to multiply this number by this atomic mass because that's for neon 20. 19.99244. And I'm going to do the same going down. I'll multiply this atomic mass by my next value. And then I'll do the same thing below that. The reason why these numbers don't exactly match up to these is because, remember, we're talking protons and neutrons have a relative mass of 1. So relatively, this is the mass number for that element. But when we talk about the exact mass, it's going to be a little bit different than that. Notice they are very close to whole numbers, just in case you were wondering about that. I'm going to solve these really quickly. And you should adhere to your significant figure rules. So I have 4 sig figs here. That's how many this number should have. I have 2 and also 2, and I have 3 and 3. And the last step is we want to add all of these up. So let's add 18.09 plus 0.057 plus 2.03. I get an answer of, now we're going to keep our significant figures again, but we have to look at least number of decimal places. So I'm going to round right here, 2 decimal places after. And our answer is 20.18 units are atomic mass units. And if you look, we were spot on to that mass, to the atomic weight on the periodic table. So this is how atomic weight is calculated. We have to keep in mind the percent abundances for each individual isotope and find a weighted average. That's what this is called, a weighted average. And just by looking at the percent abundances, you should be able to determine which atomic or which nuclide is going to be most abundant, what your weighted average is going to be closest to. If I look, most of my neon is neon 20, almost 91%. Therefore, the atomic weight of neon, the average mass of one neon atom, okay, which again really doesn't exist, your atomic weight should be closest to this mass right here, which it is because neon 20 is the most abundant. So that makes sense. And that's something you should keep in mind as you're doing these as well. The most abundant isotopes are going to have the weighted average closest to those values. That's it for this section. We will do some more practice with this in class. Of course, let me know if you have any questions. Make a couple notes in your note packet, maybe down here towards the bottom, and I will see you in the next class. Have a good day.